Hello students, in this video we'll investigate the determinant of the metric tensor and its relationship to the Christoffel symbols. Let's be given coordinates x1 through xn on space and covariant vectors EI, which are partial r, partial xi, our standard format. Then the metric tensor has the form Gij, which is EI dot EJ, our gram matrix. And we know that we're going to assume some non-degeneracy, so I want the determinant of this matrix to be non-invertible, right? With determinant of Gij, just script g not being equal to 0, okay? Now let me remind you of a few things from linear algebra which are very handy in this context. So recall, if A is Aij, I and j go from 1 to n, then the determinant of A is the sum, j goes from 1 to n, of Aij, and then Bij, where these Bij's are the cofactor matrices, right? So Bij, the Ij cofactor, okay, in other words, this is simply just the Laplace expansion of the determinant, right? But this gives me a nice result because it says if I differentiate the determinant of A with respect to any fixed coordinate, I get the cofactor, right? Hence, if I do the derivative with respect to Aij for any fixed I and j of the determinant of A, I get Bij, okay? And furthermore, we also know, get this beautiful result, furthermore, I know what? I know that A inverse times the determinant of A, when it's invertible, has to be equal to the cofactor matrix of A transpose, okay? Excellent. And so now we know what the inverse of our metric tensor is. I know what the determinant is, so let's actually write what this says in terms of the metric tensor. So hence, we know that G upper Lm times G is the cofactor of GLM, like that. Excellent. Alrighty. And so now what am I going to do? So now I'm going to consider the derivative of my determinant with respect to a different coordinate, right? So now consider partial g, partial x, let's say j, for example. Okay. So partial g, partial xj is equal to partial g, partial GLM, that number in the matrix, times partial GLM, partial xj, right, by the chain rule. Now this over here, right, we know what that is. That's the cofactor. So that's the cofactor of GLM times partial of GLM, partial of xj, right? Excellent. Now we fill in what the cofactor is. We just found it, right? The cofactor of this is just GLM times G, right? So this is just GLM times G times partial GLM, partial xj. Beautiful. So I have a derivative formula. We can actually just write this down, right? It's a beautiful formula in and of itself. As partial g, partial xj is going to be GLM. We trace over L and M, G, and then partial g little lm over xj, right? So you get a nice little formula for the derivative of the determinant of the metric tensor like that, okay? But now I can actually use a little bit more information over here. So recall that we have our Christoffel symbols, right? So what is our gamma, for example? So gamma of I, j, k is 1/2, and then g LK, and then partial GIL partial XJ plus partial GJL partial XI, then minus, not plus, minus partial GIJ partial XL, like that, okay? So now I'm going to fill in this relationship over here. So what would I get, for example, if I contracted on this K and I? So in particular, this would tell me that gamma of IJ would be 1/2, and then G, now my K is I, so that's going to be an LI, and then partial GIL partial XJ plus partial GJL, right, partial XI, minus partial GIJ over partial XL. Okay, excellent. Now, here's the key feature over here. I'm going to look at these last two terms over here in this definition of the Christoffel symbol as I'm tracing over these things. I'm tracing an I and L, right? I'm summing over I and L. I have an upper index and lower index, so I'm actually summing over both I and L, right? So if I first sum over L, then what do I see? If I sum over L, then my L and my I play the same role. So this expression over here, when I sum over L and I, zeroes out, right? And so that tells me that my gamma, I, summing over I, of course, right? J is 1/2 G, I'll put the IL first, right? And then partial GIL, partial XJ. Okay? Summing over I and J, right? So in other words, the only free index here is J, right? Everything else is being summed over. Okay, but now what do I see over here? Look at this. I see that what is this expression over here? So this is a so let's try to update the indices over here and see if we get the right sort of, the right form. And this is going to be a perfect. So this is let's use this formula over here. So this formula says that if I have a GIL and then a partial GIL, so those are the same things with respect to XJ. So I'm going to replace all the L's. So let's take this formula over here and write this as GILG partial GIL, because that's the same thing, IL, partial XJ is really partial G partial XJ, okay? And so what do we have over here? We have these first two things over here. And so this is going to be 1/2. And then if I solve for this, I'm going to take these things and replace them with this d by dg, 1 over g, of course. That's not 0, 1 over g, and then dg dxj, right? And of course, what is this? That's 1/2 the logarithmic derivative of the square root of g, right? So this implies that if I sum over I, gamma ij is equal to d by dxj of the log of the square root of g. So we get this beautiful relationship for the derivative, the logarithmic derivative of the square root of the determinant of the metric tensor over here. And of course, this is exactly the volume element, right? So I have the log of the volume element with respect to xj in terms of the trace of this Christoffel symbol with I and j. So in other words, the top index and the bottom, one of the bottom indices are the same. So I'm going to sum over that. And so I get this wonderful relationship for the derivative of the volume element in terms of the Christoffel symbols using our properties of cofactors and matrices. Thank you very much.